Well, good evening, everyone, and welcome to this event as part of the Cambridge Festival. My name is James Keeler. I'm head of department here in the Yusuf Hamied Department of Chemistry in Cambridge, and it's my great pleasure to welcome you to this webinar this evening. Before I get on to the main event, I would just like to give a little plug for some other videos which you'll find on the department website, and I think you'll find that the link is up in the chat. We've got some short videos that have been made by other members of the department covering a whole range of interesting topics. There's one about how research in the department is being used to make fuel directly from sunlight, from the Reisner group. The photonics group have a fascinating short video on how plants and animals create very vivid colors and how we can go about exploiting this perhaps in creating our own colors. There's also a short video from the Gray group about the history of batteries and some instructions there on making your own batteries from lemons. There's a very nice story called The Adventures of Ellie the Electron, which is aimed at children, which is talking about what electrons do in physics and chemistry. And also you will find the Hidden in Full View Science Trail, which is a self-guided quiz which you can follow around Cambridge. So it's my great pleasure to introduce this evening's speaker, my colleague, Dr. Peter Wothers. He's a teaching fellow in this department and also a fellow at St. Catherine's College. Now, if you've visited us when we've been putting events on for the Science Festival in previous years, you will almost certainly have seen one of Peter's fantastic demonstration lectures, which he does for us. But he's a man of many parts, and one of his other keen interests is the history of science and the history of chemistry. And he has amassed an amazing collection of books from the 16th century onwards, which describe how science, and particularly how chemistry, has progressed over these centuries. And inspired by this collection, he's recently written a book called Antimony, Gold, and Jupiter's Wolf, which is about how the elements got their names. And this is what Peter's going to talk to us about this evening. He's going to select one of the chapters from the book. And amongst other things, he's going to talk about why it is that whereas so many countries have elements named after them, not one of the countries of the UK actually has an element named after it. The presentation will last about 45 minutes. At any time, you're welcome to put comments or questions into the chat, and Peter will try and answer those at the end, assuming that there's time. So Peter, over to you, and thank you very much for offering this excellent presentation.
Right. Well, I hope that is now all working fine. Okay. Well, as you heard in the introduction there, I thought the spin that I should take for this particular lecture when working out what I was going to be talking about was why it is that there are so many elements that were actually discovered in the UK. In fact, if you exclude the radioactive elements, it's probably the case then that there were more elements discovered in the UK than in any other country. And yet, of course, the UK is the only one that doesn't actually have an element named after it. So perhaps you can think about for a moment which countries do have elements named after them. So let's have a look. So you should have come up with a few. There are quite a few, some less obvious than others. There's ruthenium, and that was actually named after the Latin for Russia. Germanium, of course, would be an easy one. Polonium, although actually curiously, when polonium was named, the country Poland didn't actually exist. Other elements, we have francium, americium. Nihonium is a more recent one, the most recent one, in fact, named after Japan. But all of these elements, no Englandium. Why not? Well, it turns out that there almost was an Englandium or something like that. And that's what we're going to look at now, why it didn't quite come about after all. And our story begins, well, not very far from here, in fact. It starts, and in fact will end, with Sir Isaac Newton. So around 1665, Newton performed his famous experiment where he shone a beam of light through a little hole in the shutters of his windows through a prism, and of course it was split up into the colours of the spectrum. He also recombined these colours to recombine to make white light as well. Well, a slight modification of this in the early 19th century by another Cambridge chap, William Hyde Wollaston, in 1802. Well, he shone the light through a tiny, thin slit instead. Now, instead of seeing the continuous spectrum as Newton had observed, Wollaston saw, well, what he took to be divisions between the different coloured parts of the spectrum. These were actually black lines in the spectrum. And you needed this fine slit in order to be able to see this, as opposed to just the circular hole that Newton was using. Well, soon after this, many more black lines were noted with finer instruments. These are now known as Fraunhofer lines, after an instrument maker who used these lines to actually help calibrate his instruments that he was making and to advertise how wonderful they are, the fact that you could see so many of these black lines. This is his spectrum here from 1814, and it just shows just how many of these dark lines are actually present in the solar spectrum. Now, with finer instruments, more lines were noted, but the exact nature of these was not understood until 1859, with the invention of the spectroscope. And this was first invented by two German scientists, Robert Bunsen and Gustav Kirchhoff. The sample was introduced on a platinum wire into the hot blue flame of the Bunsen burner, and this is actually what he invented specifically for this apparatus. And they write, "It is well known that certain substances possess the property of imparting definite colours to flames in which they are heated. When the coloured light thus produced is analysed by a prism, spectra exhibiting different coloured bands or lines of light are seen." What Bunsen and Kirchhoff saw through their spectroscope was a series of bright coloured lines against a black background. Furthermore, different elements gave their own unique spectra, and they realized that this could be used to identify what elements were present in a sample. They write, "Upon the occurrence of these lines of light, an entirely new method of qualitative chemical analysis can be based, a method which greatly enlarges the scope of chemical reactions and points to the solution of problems hitherto unapproachable." Well, the advantage of this technique for detecting the presence of elements was, over normal chemical methods, was that it was much more sensitive. In fact, they described just how sensitive this was, and they did a calculation to try and work out exactly how sensitive. They write, "In a far corner of our experiment room, the capacity of which was about 60 cubic meters, we burnt a mixture of 3 milligrams of chlorate of sodium with milk sugar, whilst the non-luminous colourless flame of the lamp was observed through the slit of the telescope. Within a few minutes, the flame, which gradually became pale yellow, gave a distinct sodium line, which, after lasting for 10 minutes, entirely disappeared." They concluded from this that it follows that the eye is able to detect with the greatest ease quantities of sodium salt less than 1/3 of a milligram in weight. They add, "In the same way, the dust which settles from the air in the room shows the bright line from sodium alpha, as they called it. To render this evident, it is only necessary to knock a dusty book, for instance, at a distance of some feet from the flame, when a wonderfully bright flash of the yellow band is seen." They introduce the idea of spectrum analysis and relate how they have analysed all sorts of things, such as minerals and even cigar ash. But their work on mineral waters was to be the most rewarding. They write, "The method of spectrum analysis may also play no less important part as a means of detecting new elementary substances. For if bodies should exist in nature so sparingly diffused that the analytical methods hitherto applicable have not succeeded in detecting or separating them, it is very possible that their presence may now be revealed by a simple examination of the spectra produced by their flames." They continue, "We have had an opportunity of satisfying ourselves that in reality such unknown elements exist. We believe that, relying upon unmistakable results of the spectrum analysis, we are already justified in positively stating that besides potassium, sodium, and lithium, the group of alkaline metals contains a fourth member, which gives the spectrum as simple and characteristic as that of lithium. a metal which in our apparatus gives only two lines, namely a faint blue one, almost coincident with a strontium delta line, and a second blue one, lying a little further towards the violet end of the spectrum and rivaling the lithium line in brightness and distinctness of outline. In a fuller report the following year, remarkably, they said, we have succeeded in discovering the presence of two new alkaline metals in addition to potassium, sodium, lithium. They occur in such minute quantities that in order to obtain a few grams of these substances, or a sufficient amount for investigation, we had to operate upon 44 tons of the mineral water from Durkheim and upon 180 kilograms of the mineral lepidolite. Well, one of these, the first of these, was named cesium. And for cesium, the spectroscope revealed two splendid blue lines situated close together and almost coinciding with the blue strontium line, strontium delta. As no known elementary body produces two blue lines in this portion of the spectrum, we may consider the existence of this hitherto unknown alkaline element as thus placed beyond doubt. They add, the facility with which a few thousandths of a milligram of this body may be recognized by the bright blue line of its incandescent vapor, even when mixed with large quantities of the more common alkalis, has induced us to propose for the name cesium and the symbol Cs, derived from the Latin cesius, used to designate the blue of the clear sky. For rubidium, this was the new element that they had prepared from the mineral lepidolite. After treatment, they observed two splendid violet lines lying between the strontium delta line and the blue potassium beta line. Will be noticed on the gradually fading continuous background of the potassium spectrum. These new lines increase in brilliancy as the washing is continued, and a number of more appear in the red, yellow, and green portions of the spectrum. None of these lines belong to any previously known body. Amongst them are two which are especially remarkable as lying beyond Fraunhofer's line A and the potassium line K alpha, coincidence with it, and therefore situated in the outermost portion of the red solar rays. Hence, we propose for this new metal the name rubidium and the symbol Rb, from the Latin rubidus, which was used to express the darkest red color. Well, it wasn't long after this that the technique was also used to find other new elements. In fact, in the same year that the technique was first announced, William Crookes was investigating some residues of a mineral of selenium. He writes, a portion of the residue introduced into the gas flame gave abundant evidence of selenium, but as the alternate light and dark bands due to this element became fainter, and I was expecting the appearance of the somewhat similar but closer bands of tellurium, suddenly a bright green line flashed into view and quickly disappeared. An isolated green line in this portion of the spectrum was new to me. I had become intimately acquainted with the appearance of the most of the artificial spectra during many years' investigation and had never before met with a similar line to this. In the purest state that I have yet succeeded in obtaining this substance, it communicates as definite a reaction to the flame as soda. This is the one that gave the bright yellow lines. The smallest trace introduced into the burn of the spectrum apparatus gives rise to a brilliant green line, perfectly sharp and well-defined upon a black background, almost rivaling the sodium line in brilliancy. It is not, however, very lasting, owing to its volatility, which is almost as great as that of selenium. A portion introduced at once into flame merely shows the line as a brilliant flash, remaining only a fraction of a second. But if it be introduced into the flame gradually, the line continues present for a much longer time. Crookes later proposed the provisional name of thallium, from the Greek thalos, or Latin thallus, a budding twig, a word which is frequently employed to express the beautiful green tint of young vegetation, and which I have chosen as the green line which it communicates to the spectrum recalls with particular vividness the fresh colour of vegetation at the present time. Well, thallium was just the first of elements to be discovered using the new technique of spectroscopy. Shortly after this, in 1863, Ferdinand Reich, a professor of physics at the School of Mines in Freiburg, began to search for thallium in some of the local zinc ores and discovered what he believed was a new element. However, because he was colorblind, he entrusted the spectroscopic analysis to his assistant, Hieronymus Theodor Richter, a decision he was later said to regret when the latter tried to claim the discovery as his own. On placing some of the process residue into the Bunsen flame, Richter observed a brilliant indigo line, which did not coincide with either of the blue lines of cesium. The new element was christened indium after this characteristic spectral line. So within the space of just 3 years, Bunsen and Kirchhoff's new technique had given rise to the discovery of 4 new elements, all of which were named after the characteristic lines in their spectra: cesium, rubidium, thallium, and indium. But before the decade was out, we could say that another element was discovered. We shall see that spectroscopy helped to find another element in 1868, but we'll skip that one for now and jump instead to 1875, when a modified form of the spectroscope revealed a new element. On August the 25th, 1875, using an apparatus that used an electric arc to heat the sample instead of the Bunsen flame, Paul-Émile Lecoq de Boisbaudron found another new element in the ore of zinc. However, this time the discoverer did not choose to name the new element after the appearance of the line spectra. He gave it the name gallium, named after the Latin Gallus for his home country, France. Well, or did he? The political magazine La Revue Politique et Littéraire was rather sceptical of his motives, and it writes, however, it seemed to us that patriotism had been foreign to the decision of Monsieur Lecoq de Boisbaudron, who had simply wanted to follow the example of the scholars of the 16th century and Latinize his name. Lecoq in Latin is Gallus, whence gallium to designate the metal discovered by Monsieur Lecoq. Well, Lecoq's biographers were anxious to point out that the metal was not actually named after himself. However, you do sort of wonder, though, that if he wanted to name the element after his country, he could have avoided these accusations by simply naming it francium, which, of course, was going to be the name of choice when Margaret Perry discovered the highly unstable last member of the alkaline group in 1939. But at this point, we need to bring onto the scene this chap. Now, you may recognize who this is from the rather characteristic hairstyle. It's said that actually he only ever had his hair cut once a year, and we can see that there are 2 different haircuts here. So hopefully you've recognized who this is, of course. It is the Russian chemist Dmitry Mendeleev, who had first published his periodic table in his textbook in Russian in 1869. And in this, he had actually predicted some new elements. But the problem was this had gone rather unnoticed. So, for instance, in England, the reception of this wonderful new thing, the periodic table, is not exactly terribly flattering. It simply says, reports that Mendeleev had proposed a new arrangement of the elements, and it lists them, the beginning of them in order, and it even gets one of them wrong. It writes the symbol Fe for iron instead of F for fluorine. So this is actually the first announcement of Mendeleev's new system in England. Nobody paid attention to it. But after gallium was discovered, well, then people did pay attention. So Mendeleev wrote that as soon as gallium had been discovered, he reminded people that he had proposed his system, and this was a systematic classification of all the elements, and that this actually could be used to correct the atomic weights of some of the elements that weren't right, but also points out that this predicted the properties of hitherto undiscovered elements. And he named these Eka aluminium. This was one space underneath the aluminium in his periodic table, and Eka boron, one space underneath boron, and Eka silicium, one space under silicon. Now, in the first announcement of this in English, the first time his paper did appear in 1879, it has a version that's slightly difficult to see these new elements and how they would fit in. They're given by the question marks here. So the question mark 44 is, well, it looks like it's 2 spaces underneath boron, and the one Eka aluminium with mass of 68, which is going to be the element gallium, looks like it's two spaces under aluminium there. But as we shall see in the Russian version of his table, it makes a little bit more sense because there's a bit of an offsetting here. In fact, we'd now say that these are 2 groups that actually Mendeleev combined into one. But we can see in the Russian table that he published, this is different version from the volume 2 of his textbook published in 1871, that he leaves these horizontal lines, and these represent elements that he wasn't quite sure about. So 2 of these, for instance, yttrium here and lanthanum, well, these were elements that had been discovered and could indeed go in these spaces. In fact, this is the correct space for them. But he also left these gaps for elements that were new. So here we find the element Eka boron, so 2 spaces, or directly underneath boron there, aluminium, Eka aluminium there, and Eka silicium there. So Eka came from the Sanskrit for 1, meaning 1 space below. At least they are in his modified form of the tables there. So he pointed out, though, in this article, that as soon as gallium had been discovered, that actually gallium is the missing element. It is the element Eka aluminium with mass of 68. And he included this in the 3rd edition of his textbook. So now, for the first time, you see the element gallium appearing in a periodic table. But soon after gallium, other predicted elements were discovered. So all 3 of these were actually named after the countries in which they were discovered. So we have our Eka aluminium, hopefully named after France as gallium there and not after the discoverer. We have Eka boron, named after the, well, Latinized version of an area in Scandinavia. So there wasn't a Latin name for Sweden itself, but Scandium perhaps conjured up this image. And finally, Eka silicium, as Mendeleev called it, well, this turned out to be, when it was discovered, named germanium, after its discoverer Winkler. Now, Mendeleev says how pleased he was that these elements were all found during his lifetime in an address given in 1889 in London. This is present to the members of the Chemical Society there. And he writes, well, the law of periodicity first enabled us to perceive undiscovered elements at a distance which formerly were inaccessible to chemical vision. And long ere they were discovered, new elements appeared before our eyes, possessed of a number of well-defined properties. We now know 3 cases of elements whose existence and properties were foreseen by the instrumentality of the periodic law. I need but mention the brilliant discovery of gallium, which proved to correspond to Eka aluminium of the periodic law by Lecoq de Boisbaudron, of scandium, corresponding to Eka boron by Nilsson, and of germanium, which proved to correspond in all respects to Eka silicium by Winkler. When, in 1871, I described to the Russian Chemical Society the properties clearly defined by the periodic law which such elements ought to possess, I never hoped that I should live to mention their discovery to the Chemical Society of Great Britain as a confirmation of the exactitude and the generality of the periodic law. However, at this time, Mendeleev still missed out mentioning one of the elements. In fact, he did say, he says, well, remember our element from 1869. He wrote, from all sides, we see attempts to constitute the imaginary substance helium, the much longed for primary matter. But he dismissed this, saying in all probability, helium should just be a form perhaps of an element that is already known and under the strange conditions of the sun. This is our element from 1868. And this is where we need to return to now to understand, well, why was this dismissed and how was this element actually first discovered? And we return to the spectroscope as invented by Bunsen and Kirchhoff, and they actually appreciated that their new technique might be even more powerful than they first thought. They write, the method of spectrum analysis not only offers, as we flatter ourselves we have shown, a mode of detecting with the greatest simplicity the presence of the smallest traces of certain elements in terrestrial matter, but it also opens out the investigation of an entirely untrodden field stretching far beyond the limits of the Earth, or even of our solar system. For in order to examine the composition of luminous gas, we require, according to this method, only to see it. And it is evident that the same mode of analysis must be applicable to the atmospheres of the sun and of the brighter fixed stars. They mention that a modification must, however, be introduced in respect to the light which these heavenly bodies themselves emit. In a memoir published by Wothers, it was proved from the theoretical considerations that the spectrum of an incandescent gas becomes reversed. That is, the bright lines become changed into dark lines when a source of light of sufficient intensity, giving out a continuous spectrum, is placed behind the luminous gas. From this, we may conclude that the solar spectrum with its dark lines is nothing else than the reverse of the spectrum which the sun's atmosphere alone would produce. Hence, in order to effect the chemical analysis of the solar atmosphere, all that we require is to discover those substances which, when brought into the flame, produce bright lines coinciding with the dark ones of the solar spectrum. What they're essentially saying is that the dark lines that we saw, that Fraunhofer first saw, and indeed Wollaston first saw in 1802, that these dark lines are actually due to where the continuum of light given out by the sun, where certain frequencies or wavelengths have been absorbed by elements in the atmosphere of that sun. So those dark lines correspond to the absorption by certain elements in the atmosphere there. And the bright lines, when we see those, well, those are the emission lines when the excited elements themselves are heated up. So there should be a correspondence. So if we look, for instance, at the spectrum here, we see what Fraunhofer labeled as lines A and B. Well, these seem to line up exactly with the lines from potassium. Well, it now turns out that that isn't quite the case, but actually each of the dark lines that we see in this early solar spectrum do correspond to known elements, or in some cases, actually molecules that could be in the Earth's atmosphere. After all, what we're looking at here is the light that is given out from the sun, which is, say, all frequencies, and then whatever is absorbed in between coming from the sun and getting into our eye, well, there must be something in between there. Some of this is due to the atmosphere of the sun. Some of this is actually due to gases that are in the atmosphere around our Earth. So now it is known that these lines actually correspond to, well, some of these are due to oxygen molecules. We have from the solar atmosphere hydrogen atoms, sodium atoms, iron, magnesium, hydrogen, more hydrogen, calcium, and even ionized calcium. So all of these things are well known, and this for the first time made it possible to actually work out what the sun might be made of. And this was, of course, for a long time thought to be absolutely impossible, because you could hardly go to the sun and scoop some up and analyze it. But here at last was a technique that perhaps gave us some idea what there was. Well, it's possible actually to look at light that comes out of the atmosphere of the sun itself. And this is what you need to do or needs to be done during an eclipse. So early astronomers actually waited for eclipses, gathered their instruments and went to the places where there would be an eclipse occurring, and then focused on the light that is visible, the halo around the sun. So usually, if you look at the light, obviously not directly, but through the spectroscope, the light from the sun, most of what you're seeing is actually from the sun itself. The light that is given out by excited atoms in the atmosphere of the sun are completely washed out by the rest of the light coming from the sun itself. But during the eclipse, you could stop seeing the light given out by the sun itself and just look at the gases in the atmosphere around the sun. And this was actually first done in 1868, when a remarkable discovery was made. And in fact, two astronomers first made this discovery, as we shall see, a French astronomer, Janssen, and an Englishman, Norman Lockyer. And, well, the spectrum here shows the normal solar spectrum with the dark Fraunhofer lines, and superimposed above this, we see the emission lines. This was the light given out by these, the halo around the sun. And so the medal that we see here, given here, has a little detail of the god Helios there, and he's pointing to these protuberances, these emissions of hot gases, and finally working out what was in these. But actually, I've sort of cheated a little bit here, because Janssen first made his discovery when looking at this solar eclipse in India in 1868. But Lockyer actually observed the light from this solar atmosphere in London at the same time with no eclipse. And actually, the medal really is celebrating a method they both independently invented that enabled observers to actually look at the light that is emitted from the hot gases around the sun. And this is really quite fun. So this is actually the actual instrument that Lockyer used that is now in the Science Museum. And in this, we can see a series of 7 prisms that are used. Now, as the light passes through a prism, the light from the sun itself, which of course is all frequencies of light from this solid body, as they are split up by each prism, they're just further dissipated each time. They're dispersed, and the intensity gradually gets less and less and less. However, the light from the hot atmosphere of the sun, where this is just one frequency, all this does, it just gets bent round. So this actually was the method that both of them independently invented, whereby they could actually look at the sharp lines from the hot gases surrounding the sun, even though it was normally washed out by all of the light coming from the sun itself. And what they observed is, we can see this in the expansion here, there were 2 little lines, the short ones that you see there, that were absolutely coincident with the lines of sodium, suggesting that there must be some sodium atoms in the vapor around the sun. But in addition to this, there was a taller line here, and this one didn't have any corresponding line that was known on Earth. And Lockyer went so far as to say that he thought this was due to a new element. And he named this element helium. Well, it's quite difficult to see where Lockyer ever actually mentions the word helium. And I'm not sure he ever did mention the word helium in print directly saying this. But it was certainly known that he did think that there was a new element there present in the sun. And in fact, it was named after the sun, Helios. The first mention we see of this was from the report in Nature from 1871 here, where it's just in a footnote where it says that Frankland and Lockyer, so Frankland helped him try to see if there was any element that was known, or if they could try to put hydrogen under extreme conditions of pressures and temperatures to try to reproduce this line. But they said they find this is hitherto unknown, and that they propose to call this new element that they thought must be here helium. This was, of course, what Mendeleev didn't like, and says, I don't believe this. And he certainly wasn't the only one. The incoming president of the British Association for the Advancement of Science in 1872 reports, Mr. Lockyer speaks as confidently of the sun's chromosphere of incandescent hydrogen and of the local outbursts which cause it to send forth projections tens of thousands of miles high, as if he had been able to capture a flask of this gas and had generated water by causing it to unite with oxygen. Yet this confidence is entirely based on the assumption that a certain line, which is seen in the spectrum of hydrogen flame, means that hydrogen also, when seen in the spectrum of the sun's chromosphere. But when Frankland and Lockyer see in the spectrum of the yellow solar prominence as a certain bright line not identifiable with any of the known terrestrial flames, attribute this to a hypothetical new substance which they propose to call helium, it is obvious that their assumption rests on a far less secure foundation until it should be received that verification, which, in the case of Mr. Crookes' researches on thallium, was afforded by the actual discovery of the metal whose presence had been indicated by him by a line in the spectrum, not attributable to any substance then known. So people doubted that there really was this element helium, and it actually took about 30 years before the element was found. But to understand this, we need to come back to Earth and look at the gases in the atmosphere again. Now, Rayleigh here, Lord Rayleigh, was investigating the gases in the atmosphere. He was trying to see whether it was the case that the mass of an oxygen atom, which we know is about 16, was exactly 16 times the mass of a hydrogen atom. Likewise was the mass of a nitrogen atom 14 times. So in order to actually determine this, what he needed to do was to determine the densities of these gases extremely precisely. So first of all, he measured hydrogen. Then he measured oxygen, and he thought that nitrogen would be a doddle, but he was quite wrong. Now, I should say that actually, when I just say he needed to determine the densities, this doesn't really quite do him justice, because in order to determine these, he needed to use an incredible balance that occupied an entire room that he built in the basement of his castle, essentially, his estate. He needed to wait overnight for the balance to settle, and he needed to observe through a window from outside the balance so as not to disturb this. But what I thought was really most remarkable, I mean, what he did was to take a glass flask and evacuate this and then fill it with the gas and then weigh it again. But what was really remarkable, that when the gas was removed from the flask, because atmospheric pressure was no longer pushing, was balanced by the pressure of the gas inside, the glass flask actually just slightly shrank, and that altered the buoyancy, and he needed to take that into account as well. So this was incredibly accurate observations here. But things went wrong when it came to nitrogen. And this was because he found that the density of nitrogen seemed to vary slightly according to how it was prepared. So on the one hand, he took some nitrogen that he prepared by removing the gases from the atmosphere, removing any water vapor, carbon dioxide, and oxygen. But he also compared this with the density that he found from nitrogen gas that was been chemically prepared. And there was a tiny difference of about 1 in 1,000 parts. But he said that this was outside the errors of experiment and can only be attributed to the variation in character of the gas. But the question is, to what is this discrepancy due? Now he needed the help from a chemist, and along came the chemist William Ramsay. Now, Ramsay thought that actually it would be possible to remove all the nitrogen very easily from the atmosphere by combining it with magnesium. In fact, he could remove all of the gases from the atmosphere, and hopefully there should be nothing left. And he did this by passing the gas, first of all removing the oxygen by combining it with copper, then removing any of the nitrogen by combining this magnesium. But what he found was that there was a tiny little residue left. And he corresponded with Rayleigh at all stages of this, and reports that eventually in August of 1894, he said that he's isolated some of this gas. Now, in this letter, Ramsay refers to his gas as X, but a few days later, he refers to this as Q, or quid from Latin for what. Rayleigh reports that he had thought of eventually calling this new gas, when it had been isolated, aeron, after the Greek for air. But he reports that when he tried using this effect privately, the answer had usually been, when might we expect Moses? Lady Rayleigh told her husband that she had heard that in a spirit of banter, Lord Halesbury had understood that the gas was known as Mrs. Harris, and this was a reference to the imaginary friend of Mrs. Gamp, one of the characters from Charles Dickens' novel Martin Chuzzlewit. So this gas was quite elusive, and they were having great difficulties finding a name. In fact, it's only recently been discovered that in July of 1894, Ramsay deposited a paquet scellé with the French Academy of the Science. And this was an accepted route when a discoverer wanted to register a claim without publishing. But this was only just opened in 2004. Ramsay described that he was guided by the experiments of Lord Rayleigh, of course, and that he'd reduced 20 litres of nitrogen down to 20 millilitres, which is about 1% of this new gas. And he says that he hopes to decide soon if this new gas is a modification of nitrogen, perhaps it was N3, or whether it's a new element. And he says that if he has made a new element, he intends to name it icazote. So this is perhaps similar to some of the suggestions that Mendeleev had, but naming after azote, or the French word for nitrogen here. So perhaps this element was meant to be like nitrogen in some way. And he ends this to this note: it should be recognised that it is to Lord Rayleigh, with whom I have been in communication, that this discovery is credited. He has shown the place to explore. I have found the means to isolate this new gas. Well, the gas was first announced at a report of a meeting of the British Association, which was reported in the Times newspaper the following day. Actually, both Rayleigh and Ramsay were working together, and they decided that they didn't want to prepare a more formal announcement because they were going to enter this new discovery into a competition in America. But apparently a newspaper announcement was okay. They checked with the regulations of the prize. And in the Times it says, well, yesterday was a busy day in the 9 sections, and one of them produced a surprise. It had been whispered about on Saturday and Sunday that an interesting announcement would be made at the meeting of the chemical section, and that the large lecture theatre of the museum was well filled at 10:30. It appears that Lord Rayleigh has been working on the densities of gases, and he has found that nitrogen derived from the atmosphere is a little heavier than nitrogen derived from various other sources. And his lordship could not explain this fact and published it with information for others. Professor Ramsay took up the matter in the belief that nitrogen derived from the atmosphere could not be pure, and he found that there is in the atmosphere a small quantity of gas which is still more inert than nitrogen. Well, the gas was not actually named at this point. It took until the end of the year for that to happen. And in the December 21st issue of the Chemical News, they reported at the last meeting of the Royal Society, it was announced that a paper by Lord Rayleigh and Professor Ramsay on a new gas, to which the name argon had been provisionally given, will be taken as a subject of discussion on January the 31st. And in the postscript for this, it says that this name was derived from the Greek for no work, or this was because the element was so inert it couldn't seem to combine with any other element at all. This symbol was, of course, later, the symbol that was proposed, A, was later changed to be in line with some of the other chemical elements in this group. But the report from the newspaper, from the Times newspaper, the first report actually didn't stop others perhaps suggesting a name. So there's a really beautiful account in a French magazine where it says that a professor at Oxford University, which wasn't right for starters, has discovered a new gas of the air. Until now, we were content with just oxygen and azote, nitrogen in the air. The Oxford chemist invents a third. There is great excitement in all laboratories of 5 continents. The name of this new gas is not yet designated, but we think that by baptizing it Oxfordgen, we will have helped find a solution that is needed. There is an ox in our proposition, and moreover, a delicate reminder of the city, now glorious, which gasifies us. And they add, when we think that humanity could live for thousands of years without knowing that the air contained different gases, we were really astounded. For 100 years, thank God, we could learn that it contained 2. And here, 5 years before the coming century, we've discovered a third. And don't think that it will stop in such a good way. Chemistry never stops. In 1950, a 4th gas of the atmosphere will be discovered. And in 1990, it will be the turn of the 5th, and so on, at the rate of 2 gases per century until at least the end of the world. Well, actually, it didn't really take that long to find these more gases in the atmosphere. Remember our element from 1868? Well, it was Ramsay who finally solved the helium riddle. A clue had been given after his first announcement of argon that someone, a chemist in America, had discovered that on heating a mineral known as cleveite, a gas was given out, and he thought this gas was actually nitrogen. It was suggested that maybe it was argon. So Ramsay went out and instantly bought all of the cleveite he could possibly find, and he started heating this up, and he trapped the gas, and then, of course, observed it with the spectroscope. And he was, of course, expecting, well, that this was going to be perhaps nitrogen, but he was hoping it was going to be argon. To his amazement, it wasn't argon, and it was the new gas. And with the help of Crookes, remember the chemist who helped identify the element thallium, he finally worked out what this gas was. And as he was looking at this, a telegraph arrived, and it said that this new element, which Ramsay had been referring to as krypton from the Greek meaning hidden, was actually helium, of all things. And this is because, well, certain radioactive minerals, and cleveite is a mineral containing uranium, when it decays, these radioactive minerals, they give out alpha particles, and these are actually the nuclei of helium atoms, and so the helium becomes trapped in the ground. So finally, at last, helium had been discovered on Earth. And Ramsay, of course, went on to isolate all the gases in this family, helium at the top, and argon, the third most abundant gas in the atmosphere after nitrogen and oxygen. But then he also detected by the distillation of liquid air the other gases, neon, krypton, and xenon. But interestingly, as soon as Ramsay has started investigating the new gas that became to be called argon, he was wondering where it might end up in the periodic table. And he actually wrote to Rayleigh at the time saying, have you thought where this could come? Now, he thought that if this was made up of molecules with two atoms combined together, then the mass was probably going to be around 20 for each atom. And this meant that it would follow nicely from fluorine. And so this is what he showed in the letter to Rayleigh, suggesting his place. Now, this is actually the periodic table from the book that Ramsay published in 1891, and he includes the periodic table here. This is a version of Mendeleev's. And Mendeleev thought that there would be 3 elements in group 8. Rayleigh and Ramsay thought that it might be possible that their new gas might actually be a mixture of 3 different gases, and this is where they should come. And if this were the case, then Ramsay proposed that maybe we should call these 3 new gases, they should be named after England, Scotland, and Ireland. They were going to have the Latin names of Anglium, Hibernium, and Scotium. But sadly, of course, it turned out to be 1 element at the time, and so didn't quite fit in there. Well, of course, they did have to go into the periodic table eventually, and Mendeleev, although initially he didn't want to find space for them, had to find space for a whole new group in his periodic table. But he made a slight error here. He put helium immediately before lithium, what we would now say in the same period, whereas actually, of course, helium should be in the same period as hydrogen. And this meant that Mendeleev thought that actually there might be 2 other elements that were even lighter than hydrogen. And these are marked by the X and the Y in this version of the periodic table here. And he proposed to call these elements, well, one he thought was going to be found, had already been detected again in the atmosphere of the sun, and he proposed to call it coronium. But the other one he thought he would name after Isaac Newton and call it newtonium. But that's where I need to finish. Thank you very much.